All right, next we're taking a look at the next section in this chapter, properties of curves. We're looking at increasing and decreasing functions. We have a couple of objectives. We're going to find intervals on a function where they're increasing and decreasing using derivatives and sine graphs and everything like that. And we're going to understand the idea of monotonicity and strictly increasing and decreasing functions through the use, again, of sine diagrams and graphs. So we're taking everything we've been talking about with derivatives and applying it now. So basically, the idea here is that when we talk about what they're increasing or decreasing, we're talking about over intervals. So we're going to be focusing on these algebraic forms of how we write the intervals that we're focused on for these particular things, again, when they're increasing or decreasing. Now, a couple of statements here we want to be aware of. It says f of x is increasing on s, where s is just any value of x here. And these double-sided arrows, they stand for if and only if. And it reads here, f of a, meaning the y value at a, is less than f of b, the y value at b. For all a, b, such that a is less than b. Basically, the idea there is that if I have some point a and some point b, if it's going up from a to b, then we say the function is increasing. Obviously, the opposite is true there. It's decreasing if it's doing the opposite. So just like the previous video where we were talking about not hard concepts, but just taking derivatives and then applying them. Now, you want to be careful about the fact that we're talking, say, in this particular example, when we have x equals 0. At x equals 0, we know the derivative at that point is 0. But when we talk about where the function is increasing or decreasing, well, since I'm going from left to right, it's decreasing over that interval there. So we say y equals x squared is decreasing for x is less than or equal to 0. But we also come in and we say that it is increasing for all x is greater than or equal to 0. Don't get bogged down in the fact that we're talking about that x is equal to 0 part, because it's not really changing anything. It's just telling us that over that interval, that's what's happening. All right. Now, we have a couple of other important things here. In this particular slide, we're focusing on the word strictly increasing or strictly decreasing. When we say a function is increasing, well, then it could be greater than or equal to. The derivative could be greater than or equal to 0 at that point, because that's what the derivative is. It's the slope of the tangent line at that point. But if we're saying strictly increasing, now we're not including 0 into that inequality there. You have to say the derivative has to be exactly positive. Okay? And the same thing for decreasing. If it's just decreasing, the derivative can be less than or equal to 0. But if it's strictly decreasing, then it has to be negative. Can't include 0 there. So small but important. All right. Now, monotonicity. Monotonicity is the idea that you're always increasing or always increasing. So this function on the left here, y equals 2 to the x, that's always increasing. It's just going up and up and up, never going down, always increasing. The one on the right, that is monotone decreasing 3 to the negative x, because it's always going down. So it's different than the idea of strictly increasing or strictly decreasing. It just means that mono meaning one, meaning it's always doing the same thing. It's either always increasing or always decreasing. We talked about strictly already, so we're good there. Okay, so let's look at an example. It says find intervals where f of x, which is this function over here, find where it's increasing and find where it's decreasing. Well, if I look at it here, if I started on the left and I started following the curve, it looks like it's increasing there. And in fact, it is. So I could say that it is increasing, f of x is increasing, for all x is less than or equal to -1, because there's my -1 value. But that's not the only point where it's increasing, because it's also increasing over here on the right. So I could also say it's increasing where x is greater than or equal to 2. Well, what's happening in between? Well, in between, it's going down. The function is decreasing. Its derivative would be negative. So we say it's decreasing on the interval -1 is less than or equal to x is less than or equal to 2. Pretty straightforward stuff. Now, sometimes it's not quite as easy, and sign diagrams will help us out. But when we talk about sign diagrams, we're talking about the sign diagram of the derivative. We've talked about sign diagrams for functions before to talk about zeros and everything like that. But now we're talking about sign diagrams for the derivative. So the derivative we know for this function, f of x equals x squared. The derivative is 2x. So the key point that we're going to put is wherever the derivative equals 0, obviously that value is 0. And then all we want to do is we want to figure out what are the signs of the derivative on either side of that. So just pick a point. So I could say at -1, for instance. If I plug -1 into this derivative function, I get a negative value. That's why I see negative there. If I plug in a +1 into the derivative value, I get a positive value. Now, what that allows me to do is that allows me to come in and say, all right, now that function f of x equals x squared, it's going to be decreasing when x is less than or equal to 0, because I had that negative value there, and it's increasing when x is greater than or equal to 0, because I had the positive there. The same could be said for the next function when we have f of x equals -x squared. It's going to be the same point on that sign diagram, meaning we have 0. But when you plug in points, you end up getting a positive and then a negative. So we say the opposite there. We say it's increasing when x is less than or equal to 0, or decreasing when x is greater than or equal to 0. If I'm going too fast, feel free to stop and rewind and watch again, because I'm about to get into some slightly more challenging examples. Now, if we look at f of x equals x cubed, the derivative we know is 3x squared. Again, still only at one point we have to focus on 0 in the middle. But what happens here is if you plug in a -1 into that function, you end up getting a positive value. Oh, sorry, not into there. If you plug in -1 into the derivative function, you get a positive value. If you plug in +1 into the derivative function, you also get a positive value. So what that means is that the function is always increasing, or the derivative is never negative. And what that means is that it's monotone increasing. Now, if you just said it was increasing for all x, where x is an element of the real number set, that's saying the same thing. So don't worry so much about that. Look at the next example. We have x cubed minus 3x plus 4. We have the derivative function as 3x squared minus 3. Just a little bit of factoring gives us zeros of that derivative function of -1 and +1. So those are the values that are going to go into our sign diagram, -1, +1. Check points, and again, we're checking points by plugging them into the derivative function. We see positive when we plug in, say, -2. We see a negative when we plug in 0. And we see a positive when we plug in, say, 2. All right? So based on that, we can say that the function is increasing when x is less than or equal to -1 and greater than or equal to 1, and is decreasing in the middle. So again, increasing for x is less than or equal to -1 and greater than or equal to 1, decreasing when -1 is less than or equal to x is less than or equal to 1. So again, we're using the derivative to understand when the function is increasing or decreasing. All right, so let's do some on our own here. We have our function right here, -x cubed plus 3x squared plus 5. We're going to say, let's find that derivative. That's going to be -3x squared plus 6x. We want to know, oops, I've got my squared. Now we're going to know, when is this derivative equal to 0? Well, what can we pull out? We can pull out a -3, -3x, giving us x minus 3 on the inside. So the zeros for the derivative are going to be 0 and 3. 0 and 3. And then just check some points. Again, where are we checking? We're checking them into the derivative function. And when you do that, you end up getting negative, positive, negative. So we say f of x is increasing for 0 is less than or equal to x is less than or equal to 3. And it's decreasing for x is less than or equal to 0 and x is greater than or equal to 3. Okay? No big deal. We kind of understand what's going on. Now, I'm not going to do example B fully, but I'm going to show you one thing that's going to happen sometimes. I'm just going to show you what the sign diagram looks like. There's 0 and 2, and we end up getting negative, negative, and positive. And that's going to happen sometimes. We'll get into why that is, what that means for what the function is doing in just a couple of sections. But for now, all you need to understand is that we say it's going to be increasing for x is greater than or equal, oops, I wrote it the wrong way. For x is greater than or equal to 2 and decreasing for x is less than or equal to 2. Okay? Again, we'll talk about why that is that we had that negative and then negative and the sign didn't change in between there in just a little bit. Okay. And you see there a couple of graphs on top, and you could pause and think about why that is for right now. But like I said, for right now, we're just talking about what it means to have those values there. One more example that we want to talk about for this section here, talking about this f of x value, and we're going to show that the derivative is this guy right here. Obviously, we're going to be using the quotient rule, and we're going to draw a sign diagram, and then we'll find instances where it's increasing and decreasing. So it's a good review for us with the quotient rule. We can go ahead and say, all right, if that's f of x, we know u is 2x minus 3, and u prime is 2. We know v is x squared plus 2x minus 3, and v prime is 2x plus 2. So when we go to find f prime of x, u prime v is going to be 2x squared plus 4x minus 6 minus uv prime. And I'm just going to go ahead and multiply that out, save us some time, and that's 4x squared minus 2x minus 6 all over 2x minus 3 times 2x plus 2 quantity squared. You might be wondering why I'm not multiplying that out. Well, because I know that eventually is going to not even matter because that part's going to be 0. So let's just do some simplifying on the top. When I simplify on the top, I end up getting negative 2x squared plus 6x, and then the bottom 2x minus 3, 2x plus 2 squared. Now, like I said, the reason that that doesn't matter what the denominator is because when we want to know when the derivative equals 0, that's going to end up canceling it out. Now, we did show, by the way, that the derivative was what they claimed it was, so we're good there. I mean, I didn't factor out the top of that. That's the same thing. Now, what I want to do is I want to know when it equals 0. Let's bring that up a little bit. So now I have, if I just cross multiply, that makes the whole denominator go away. So that's what I was referring to before. So I have 0 equals negative 2x, x minus 3. So x equals 0 and 3. Now we can get into the sign diagram. There's 0, there's 3. Plugging into the derivative function, I end up getting negative, positive, negative. So you can see it's increasing when 0 is less than or equal to x is less than or equal to 3. And it is decreasing over here and over there. All right. So hopefully that helped you out with understanding how to determine whether functions are increasing or decreasing using derivatives. And didn't mean to push that. And that's it for this video. All right. See you next time.